My name is Toan, and I'm engineer student at INSA Lyon, and I'm currently working on my final year internship at Ampere Laboratories at INSA. And today I would like to present to you my project for this internship. It's about the application of deep learning and stereo vision in aphid detection. So for the context, in agriculture, aphids are among the most destructive insect pests on cultivated plants in temperate regions. And in addition to sucking sap of the plant, they are major transmitter of crop infecting viruses, and it's not easy to control them. And in industrial scale agriculture, we must rely on pesticides to deter aphids from spreading the virus. And the use of these chemical substances has led to alarming consequences to public health, to the environment, and even to the economy. And although there are already some biological ways of fighting aphids, like the use of ladybugs, but they are still inefficient in large-scale farming. So aware of this problem, a laser pest control method is the main idea of the RINSEAL project, the project that I'm currently working on. It's aimed at reducing the use of pesticide by developing a module to be embedded on a vehicle robot to fight against crop aphids. And the technique is based on deep learning, object detection, and stereo vision. We use in this robot two cameras, one at the front of the robot to detect plans for automatic navigation, and another attached in the chassis of for aphid detection. So and this camera also capture the depth of the depth channel of image so that we can locate objects in 3D coordinates. For the laser module, the laser is controlled by a very fast and precise system. It consists of two miniature mirrors which can be rotated to deviate the laser beam in the correct direction. And the laser shoot will be triggered when the deep learning model detects an aphid, and the beam will overheat the target to harm it sufficiently. So overall, when mounted on mobile robots patrolling through crop fields, system will scan the plants and find accurate location of aphids. And this new means of fighting will settle a new sustainable way of pest control to better combat them. So my task in this project at Ampere Laboratories is to find optimized algorithms for plant and aphid detection on embedded system, and also to improve the lighting system of the robot. For the aphid detection part, the first thing we need to do is to create an ideal lighting environment, because our vision system is too sensitive to outdoor varying light conditions. So we want to isolate the plant and the camera in a dark chamber at the bottom of the robot. And we control the light in this chamber by installing a LED system on the top. And with this system, we can have a stable environment, and we can also use it as a laser protective housing. And we also adjust the camera setting in order to maximize the contrast between eyes and leaves. For the neural network, for the detection algorithm, I use YOLO version 4 as the deep neural network because of its efficiency and its excellent inference speed in real-time detection. And for your information, YOLO V4 is a deep neural network which uses CSP.NET as the backbone and a multi-scale feature detector to recognize objects in image. However, our problem is quite complex because aphids are very small on image. So we need to crop a region of interest in the image and tile it into small blocks in order to zoom the image and increase the accuracy. To interact with the camera and the laser, we implement this detection algorithm on a Jetson AZX. It's an embedded AI computing platform developed by NVIDIA. And some improvements that I have made to YOLO V4 to detect small objects better. The first thing to do is to add higher stride convolution upsampling to improve the receptive field of the network. The receptive field is defined as the size of the region in the input that produce the feature in virtual map. The second thing is to use an optimal loss. In our application, we don't care about the size bounding box. The only thing that matters is the center of the box. So I use distance IOU loss to optimize the model in training. So this loss will help to minimize the distance between the center of the predictive box and the target box. So the model can converge much faster in training. And the third thing is, as I have mentioned before, tiling image into small block to increase the accuracy. And furthermore, for embedded system, this model is optimized by the TK-DNN library, which quantifies all layers of the network in 14.16 format, so it can do inference at higher speed. Overall, with this configuration, we can reach about 66% of accuracy and for about 18 to 20 FPS overall when inference with batch of 4 on Jetson Xavier AGX. So this is our result. This is the original video and the video inference by Joel before. As you can see on the red dot on in the video, Aphid detected by algorithms, and this point will be captured in 3D coordinates by the 3D camera to point the laser precisely at X location. So for conclusion, even though we haven't finished the prototype yet, the test in laboratories show some very promising results. And in the future, we hope that this project will help to control not only aphids, but also on the pests in general, and so that we can reduce the use of pesticides in agriculture and furthermore limit the consequences to public health and to the environment. So thank you for your attention.